joint central moments, covariance, correlation coefficients, and the properties of covariance. So, in today's class, we are going to discuss about joint characteristic function, joint moment generating function, Gaussian random variables, properties of Gaussian random variables, and linear transformation of Gaussian random variables. These are the learning outcomes of this present class. So we'll go for the class. Here, wait. Is it audible? Is it audible and visible?
No, sir.
Is it audible? Okay. Wait a moment. Wait a moment. Now is it visible to you people? Is it visible? Is it visible?
No, sir.
हमारा स्क्रीन కనిపిస్తుందండి.
లేదు సార్.
Okay. Now is it visible? Is it visible now?
No, sir.
Yes, sir.
No, sir.
ఒకసారి చూడనా?
లేదు సార్.
ఒకసారి మొబైల్ కానీ సిస్టమ్ కానీ రిఫ్రెష్ చేయండి ఒకసారి. అంటే ఓన్లీ స్క్రీన్ పెట్టినానండి, ఇంకా ఏం రికార్డ్ ప్లే చేయలేదు.
అనిపిస్తుంది సార్. Yes, sir.
No, sir.
What about others?
Yes, sir. We can see.
Can you see that? Can you people see that one?
Yes, sir. Yes, sir.
Start. Can I start that? Can anyone give me response? Can I start that?
Yes, sir.
On probability theory and stochastic process. In the previous lecture, we have discussed about joint central moments, covariance, correlation coefficients, and properties of covariance. And in today's class, we are going to discuss about some new topics. That is joint characteristic function, joint moment generating functions, Gaussian random variables, very important one, and properties of Gaussian random variables, along with the linear transformation of Gaussian random variables. That means by end of this lecture you are going to know about, or you are going to learn all these things. That is a joint characteristic function, what is a joint characteristic function, and what is a joint moment generating function, and what are Gaussian random variables, how they are used, and what are the properties of Gaussian random variables, when and where we are going to use these properties, along with the linear transformation of Gaussian random variable. So coming to the first one, that is joint characteristic function. See, the joint characteristic function of two random variables, capital X and capital Y. Previously we have discussed about the expected values like that. So we have a joint characteristic function, which will be a function which will be for both the random variables. Here, let us consider that the joint characteristic function of two random variables, capital X and capital Y, is defined as the expected value of the joint function g of x comma y. Previously we have seen that g of x comma y is equals to, in terms of independent random variables, g of x comma y is equal to expected value of x comma y, which will be equals to product of a individual expectations, that is e of x and e of y. And here the joint characteristic function of the function g of x comma y will be equals to e power j omega 1 x into e power j omega 2 y, and it can also be written as xy of omega 1 omega 2. xy of omega 1 and omega 2 is equals to expected value of e power j omega 1 x into e power j omega 2 y, and which will be equals to e power of j omega 1 x plus j omega 2 y. Okay, where omega 1 and omega 2 are the real variables. Okay, that means you are taking only the real values here. We are not taking any imaginary values here. Therefore, it can also be written as the joint the characteristic function is also can be written as xy of omega 1 into omega 2. Omega 1 omega 2 is equals to integral minus infinity to infinity for x value and integral minus infinity to infinity for y value, e power j omega 1 x plus j omega 2 y into function of f of x comma y with respect to x of y into dx dy. And this is also known as the two-dimensional Fourier transform. I repeat, this is also known as the two-dimensional Fourier transform with signs of omega 1 and omega 2, and are also called as the and also are the reversed for the joint density function. That means the values will be reversed for joint density function. So the inverse Fourier transform of the joint characteristic function gives the joint density function. In previous sessions we have discussed about the capital PDF and small PDF. Okay, in the same sense here, the inverse function, the inverse Fourier transform of the joint characteristic function, the inverse Fourier transform of the joint characteristic function gives the joint density function. Again, the signs of omega 1 and omega 2 are reversed here. That is, the joint function, the joint density function fxy of x comma y is equals to, here, see here, in the previous sessions we have discussed about capital PDF and small PDF, and here the inverse Fourier transform of the joint characteristic function. I repeat, inverse Fourier transform of the joint characteristic function gives us the joint density function. Okay, and again the values of signs of W1 and W2. W1 and W2 are reversed. Here W1 and W2 are real values. Okay, see here. Though in two-dimensional Fourier transform, that means in a density function also, W1 and W2 all values are reversed. That means the real values are reversed. In the same sense here also, in order to find the joint density function, the value of, that means the real values are all again they are also reversed value, and we can mention that one as, or we can represent that one as fxy of small fxy in sense density function. fxy of x comma y is equals to integral minus infinity to infinity, integral minus infinity to infinity g of xy omega 1 omega 2 into e power minus of, here we have taken plus of, and here we are taking minus of, inverse function of minus j omega 1x plus j omega 2y into dou omega 1 into dou omega 2. Okay. So coming to the next one, joint moment generating function. So joint moment generating function. Here in the previous section we have discussed joint characteristic function, and here we are going for joint moment generating function. That means both x and y are jointly generating a moment. That means an outcome. So the joint moment generating function of somebody is talking. Please mute your mic. Somebody is talking. Please. I don't know who is that. Somebody is there. Please mute your mic. Everybody, please mute your mic. Two random variables x and y is defined as the expected value of the joint function. Expected value of the joint function g of x comma y, which will be equals to e power theta 1 x into e power theta 2 y, and it can be expressed as capital M instance moment xy of theta 1 and theta 2 is equals to expected value of e power theta 1 x into e power theta 2 y, which will be equals to, it is the power of a power m into a power n. That can be written as a power m plus n. That means e power theta 1 x plus theta 2 y, where theta 1 and theta 2 are the real variables. In the previous slide we have taken that w1 and w2 are the real variables, and here we are taking theta 1 and theta 2 as the real variables. Therefore, mxy of theta 1 and theta 2 will be equals to integral minus infinity to infinity into integral minus infinity to infinity e power theta 1 x plus theta 2 y into fxy of x comma y into dx dy. So here we are generating a distribution function. In order to obtain density function, this can be integrated with respect to theta 1 and theta 2. See here, and the joint density function is given as fxy of small fxy of x comma y is equals to integral minus infinity to infinity integral minus infinity to infinity capital M x y of theta 1 theta 2 into power minus of inverse of theta 1 x plus theta 2 y with respect to d theta 1 and d theta 2. So previously we have taken, as in the previous session we have this here, see here, we have taken the inverse value minus of. In the same sense here we are also taking the value of minus of theta 1x plus theta 2y. Okay. So see here, Gaussian random variables. So for two random variables, if two random variables x and y are said to be jointly Gaussian, here we are discussing all about the joint moments and joint terms. So if two random variables x and y are said to be jointly Gaussian, then the density function can be written as fxy of x comma y is equals to 1 by 2 pi into sigma x into sigma y into root of 1 minus p square into exponent of minus 1 by 2 into 1 minus p square into small x minus capital X complement whole square by sigma x square minus 2p into capital X minus capital X complement small into small y minus small y capital Y complement by sigma x sigma y plus small y minus y capital Y complement by sigma y square. Okay, it is a minus p whole square form. That is a x minus capital X, small x minus capital X square minus small x minus x complement minus small y minus y complement whole square. So, okay, and this is also called as bivariate Gaussian density function. This is also called as bivariate Gaussian density function. That means here we are using two values, that is x and y. So this is also called as bivariate Gaussian density function. For n random variables, here we have considered only two random variables. If you want to consider that for n random variables, that is n n random variables n random variables for a jointly Gaussian can be defined as, see here, density function can be defined as f x1 x2 so on xn. Here we are not taking the y value. Here we have taken only one value, that means consider n random variables xn. We are taking only one literal here, or one variable here xn, where n equals to small n to n. Then they are said to be Gaussian, jointly Gaussian if their joint density function n variate density function is given by, it has to be in this form. It has to be in this form, given by f suffix small x1 x2 x3 so on xn of x1 x2 so on xn is equal to 1 by 2 pi whole power capital N by 2 into modulus of Cx whole to the power of 1 by 2, or we can write as a root Cx into exponential form of minus of capital X minus x complement whole transpose into Cx power minus 1 into capital X minus x complement by 2. And where the covariance matrix of n random variables. So this covariance matrix, that means we need to find this Cx covariance matrix. That means we have seen already C11 or C20, C02, C11 like that. In order to find the covariance matrix, that is here we have taken only one variable, that's why Cx is equals to C11, C12, so on C1n to Cn1, Cn2, so on Cnn, and x minus x complement will be given as x1 minus x1 complement, x2 minus x2 complement, so on xn minus x1n complement. We have taken n random variables. Okay, so x minus x complement whole transpose is nothing but a transpose of x minus x complement. Here mod of Cx is the determinant of Cx, and Cx inverse, this one, this Cx inverse is called the inverse of the covariance matrix. And the joint density function for two random variables x1 and x2 can be derived by substituting n2. N is equal to 2 in the formula of n random variables. Suppose if you want to find out the two variables, that means here we have taken only n random variables. We have taken n random variables. If you want to find for two random variables, that is x1 and x2, substitute the value of n is equals to 2 in the above formula. Then we are going to find in this here, where if you substitute 2 here, then we are going to find out the Gaussian density function for two random variables, that is x1 and x2. And coming to the properties of the Gaussian random variables. First one, the Gaussian random variables are completely defined by their means, variance and covariance. That means this Gaussian random variable value will be defined completely based on three parameters, that is their mean values and their variance values as well as the covariance values. That means how they are being notified in order to find the values. That means in order to find the Gaussian random variables, see the Gaussian random variables are completely defined. These Gaussian random variables are completely defined by their mean value as well as covariance and variance value. Okay, coming to the next one. The Gaussian random variables are uncorrelated. That means here they are correlated. That means if they are not proper, if they are not in a proper way, then they are statistically independent. If they are correlated, then they are statistically not independent. If they are uncorrelated, then they are statistically independent. That means then they don't. One function will not depend upon the other function. That means the outcome of one variable will not depend on the another variable. Coming to the next one, all marginal density functions derived from n-variant Gaussian density function are Gaussian. So here we are finding some marginal density functions. So all marginal density functions derived from n Gaussian density functions are Gaussian. So we are finding some marginal values by using this n-variant. We are deriving some Gaussian density function from n-variant Gaussian density function are Gaussian. Okay. So the next one, all conditional density functions are also called as Gaussian. Whenever we are finding a signal or we are finding any information or any value, that must undergo some condition only. Okay. Last one, all the linear transformation of Gaussian random variables are also Gaussian. So even though it may be it may not be a Gaussian random variable, all the linear transformations, whatever we are converting from a non-linear to linear transformation, it also comes under Gaussian random variables. So see the linear transformation of a Gaussian random variables. See how they are being converted. Consider n Gaussian random variables y1, where n equals to small n equals to y to capital N, having a linear transformation with set of n Gaussian random variables xn, where n equals to 1 to n. Then the linear transformation can be written as say here y1, y2, y3, so on, yn is equals to a11, a12, a1n up to ann of x1, x2, x3, so on, xn. Then the transformation t is equals to, here the transformation function t is a11, a12, so on, a1n2, an1, an2, so on, ann. Therefore, y is equals to transformation function into x value, and also with the mean values of x and y, which will be equals to y minus y complement is equals to transformation function into x minus x complement. And if you want to find the value of x, then x minus x complement equals to inverse transformation into y minus y complement. Inverse transformation into y minus y complement. So by this class we are going to end our theory part of this chapter 2, and some more information is there. I will provide it in the next class. Thank you. Only 34 participants are there. Only 34 participants are there. And, have I given you any assignment in the past class? No assignment teacher only. Last class
No, sir. No,
Okay,
sir.
Nana. Second chapter complete. Okay. Second chapter complete.
Late, sir.